Hello everyone. So basically we are going to study today uh, drift velocity. So it comes under current and electricity. So what do we mean by drift velocity? See, whenever we talk about a conductor, there are free electrons present there. So when the electric field is not applied on the conductor, how do we apply the electric field? Through the help of a battery. You know? So when the electric field is not applied to the conductor, let's assume this is a wire of cross-sectional area A, right? So for now, consider there is a battery and that is disconnected, right? So whenever it is disconnected, the electrons are moving randomly, okay? The electrons are not moving in a particular direction because it is disconnected and they are free to move anywhere, right? But when we apply a desired voltage or a particular electric field in a particular direction, then the electrons move, right? So let's make the circuit closed, right? So this is how it works. So this is plus, this is minus. So the electric field direction will be this side. So the electrons will move this side, right? So what I am talking about is first the electrons were moving randomly and now the electrons are moving in a particular direction. And this here, the velocity at which they will move is known as drift velocity. Okay. So here, first of all, we are going to understand and derive a formula for the drift velocity, and then we are going to derive the formula for the electric current with the help of a drift velocity. And we are even going to study the mobility, although this is not related to this chapter, that is more important for the semiconductor chapter. Okay, let's cover the drift velocity. So, as told by me, that the electrons will move randomly when electric field is not applied. So, let us consider that there are many electrons, and for them, the initial velocity be u1, u2, u3, and so on, right? And we know that the force which is equal to ma can also be written in case of electric field as EE, where E is the charge of a single electron and capital E is the electric field, right? So here what happens? We can equate this to find the acceleration for a single electron due to this electric field, right? Now we know the equation of motion, which is V is equal to U plus AT. So as there are many electrons, so we can say for all the electrons, V1 is equal to U1 plus AT1, V2 is equal to U2 plus AT2, V3 is equal to U3 plus AT3, right? This way we can go for up to n electrons, the number of electrons which are present there. But is it possible for us to calculate for each and every? So what we are going to do, we are going to calculate for everyone and divide it by the total number of electrons to get an average value, right? So once we do that, you're gonna get the drift velocity. But there is a lot of catch here. Let us hold on to that. Okay. So we are going to divide it by the number of electrons present there. So similarly, this will happen in the case of initial velocities also, right? Plus, as the acceleration is constant, but the time is not constant here. So I'm taking acceleration as outside and t1 plus t2 plus t3. I have not defined many things here. I'm going to tell you more. So see, now let's break this equation more. See, when we talk about initial velocity, as the electrons were moving randomly when the electric field was not applied, we can take the entire vector sum to be zero, right? We can take the entire vector sum to be 0. So this comes out to be 0. So we are left with this. So this is what is our drift velocity, average drift velocity, which we want to calculate, which is equal to 0 plus a t1 plus t2 plus t3 and so on up to tn by n. But now there is a catch here also. How? This time is not a simple time. This is the relaxation time. What do we mean by relaxation time? The electrons collide. The electrons collide. And the time they collide between, मतलब the time between two successive collisions. मतलब first one electron collides with, this is first electron, this is second electron, this is third electron. The first electron collides with the second electron and then it is collides with the third electron. The time between the collision of second and third electron is known as the relaxation time. So we have calculated the relaxation time for n electrons. So we are dividing it by n to get the value of average relaxation time. Okay. So this comes out to be T. Generally, it is referred by tau. Okay. This is referred by tau. So we get a formula for drift velocity and we have calculated the acceleration. The value of acceleration is E by m into tau. So this is our drift velocity. Okay. So let's move on and derive a formula or establish a relationship between current and the drift velocity. So as we found that drift velocity is there for the electrons, and we know that what is current? Current is Q upon P, right? Charge upon time, right? So let us assume that there are n number of electrons, n number of electrons per unit volume, right? And let's the area, let the area of the cross section be A. Okay. So what will be the total charge present inside this? What will be the total charge present inside this? And let this length be L. The total charge will be N into volume of the conductor into charge of one electron, right? This V is the volume of the conductor. But how do we find the volume of a conductor? By multiplying the area of cross section into the length, right? This A and L. So N into AL into E, right? So this is the value for Q. So why did we multiply volume? Because we didn't take N as the number of electrons present there, but we took it as a number of electrons per unit volume present there. Okay. So this is the difference between means generally we take N and here what we have taken as. Okay. Now we have found the value of Q. Now we need to find the value of T. So time, can I say the time as length upon drift velocity, right? The charges are going from one place to another, one end to another end. So they what will be the time taken by them? It will be L upon the drift velocity, right? So now we find current I is equal to Q upon T. So this becomes NAL E by L upon VD. LL cancels out. So this becomes NEA VD. Okay. So this is a very important formula for current. Okay. So you need to remember this formula. From here, we can derive many things like I is equal to ENA VD, right? So we can just divide current by A. So we get I upon A is equal to EN VD, right? So we get current density as EN VD. Here, one thing is to be noted, I was putting, if you recollect, I was putting a vector sign here, but I then erased it. There is a story behind it, but I will not tell it right now, you know. But here, the current density is a vector quantity and the drift velocity is a vector quantity. So we have mentioned the same, right? So this is about the drift velocity.